Simple message, don't overthink. That's a typical mistake in does. Just because it's an exam, you will try to overthink. Somebody will come and give you the current year. But take your white sheets.
So we will bring the sheets.
Yeah, white sheet is from the office. There are 4 questions in the exam. Depending on the marks attempted probably. Don't go beyond 6. If you're going beyond 6, that means you're not getting it. So it's okay. Last time, somebody told me, you had something called indicative value. Necessity and sufficiency. Value is necessary. Right. So yeah, yes. And for one differentiable column. Last time, let's take the example. There's 2 examples. Example, very simple example. Summation. You can also do it. 1 x. It is a vector analysis. What is this problem look like? This and move that minus, minus it's to max of love. Alpha is essentially again all the different users. Okay, so what should be the KVP condition for this? To the right KVP condition here is P1. There's the X. So the KVP condition. Greater than 0. Why it's Okay, so for this problem, what will be my, so associate with respect to xi greater than b, you want to associate one kind of just to this situation. What is your for this lambda? Let's call this. Will be single just forecast. Oh, so what are that? The conditions.
Lambda is zero.
Lambda is
Data equal to 0. Summation lambda equals to me.
summation lambda I.
Summation lambda I minus 1. That is equals to me, right?
That's not my case. No, equality is an equality.
You want that?
You know that's something. That's the one. Be my data. We differentiate this. What is the difference of one one? The other one is not the same. We should do the minus. But the minus is bad. What else?
Plus minus 7.
Yes, ma'am. So, let's solve this. Now, so if I can find such a solution, then I'm getting this stuff. That's what my database. It's all the difference. So, we just stare at it and try to tell me what should I do.
All of the x's cannot be 0 because you have a condition that summation is equal to 1. So whenever the x's are non-zero, the lambda I should be 0 by the third condition.
Yes.
So for those subset, index set subset for which lambda is are 0, we can get the alpha mu in terms of alpha I.
But how do I identify them first? What you're asking is correct, but how do I identify which one's 0, which one's not 0? Because there are two variables here, right? Lambda I as well as mu. But can you represent all of these as just one condition? Equations over just one variable? Currently, there are two of them. But is it possible to represent it as a function of just one variable. What is 3 and 4 tell you? 4 tells you something about writing lambda in terms of mu and x. So I could essentially write lambda is equal to simply minus of this 1 by alpha I plus xi plus mu I and put it back into 3 so that I get rid of 2 variables. And then I can start working with this one variable. Okay, suppose that I do now working with it. Lambda is in the example. Now we will be here. Will be xi times mu minus make sure that what I write is right. All I've done is just substituted for lambda, and this is my new complementary system. Now, what can we deduce from this? This has to be true. Product of 2 variables. Now, I want to extract some extra information given that this. What is the extra information?
If xi is not 0 for any of them, then it is better be xi is mu minus alpha I for each child.
One more calculation. That is lambda I is greater than or equal to 0, which will imply that put it. Then I take this as a function of lambda over here. This plus this, and because I know that lambda is greater than 0, gives me an additional fact, which is
Mu plus definitely plus mu plus 1 by alpha plus
minus 1 over 5 plus this is 2 minus. It will be equal to 2. So use that. So I need 2 equations, right? Now I need to figure out what are the values of xi and use this then satisfy all the equations. Right? So now you have to use all your information about the problem. What is the problem you're looking at? Okay. Your intuition can also help you.
alpha I plus xi would have greater than 0.
Xi itself is greater than 0. Alpha I by definition are greater than 0, otherwise I can't even take law. Alpha I given to me here.
Okay, so we are solving a minimization problem, right?
Yeah, max of.
Yes, so basically, we don't want to get tends to minus infinity. We
It
are
can never get to minus infinity because summation of xi is 1 and alpha is greater than 2. Even if you assign 0 weight to a particular I, you still give something. So it's not going to go to minus, don't worry about it. Only interested in finding this with the existing solution. These equations. I gave you the answer last time. You can remember that will give you some intuition as to how to solve this. We said the answer about that thing. So, okay, what I wanted you to think about larger alpha will get a larger xi or smaller alpha will get a larger xi. That's what I wanted to think of. But the real thing about max. So suppose alpha I was larger, Would you like to put larger xi there or smaller xi? Right?
Because the difference will keep decreasing as log.
Because log is a concave function, so you would want all components to have equally large values so that you can maximize the sum of the logs. You'd like to raise each one's level rather than assign all of it to just one and rest of them 0. That you can argue very quickly that just one x1 will not be 1 unless the alphas are so bad somewhere else. Okay, so now given that we have this extra information, how will we solve this problem?
None of the x's will be 0, so lambda should be 0.
That's one. I drew the next picture last time, if you remember. Some of the x's will in fact be 0. If I would like to alpha I, so think of one, so throw the alpha I, yeah, so that's why it's bad. If it was log of 1 plus alpha I xi, it's much easier to develop mutation. Rather than alpha I plus xi. So then you don't want to assign it to indices I for which alpha is very poor. Yeah, let's stick with this. So yeah, after all this, you come to this. These are the two equations you really want to take out. We get some insight from this to get it on. So let's take conditions on mu. When will the equality be true? On equation 2.
It's equal to 1 by mu minus alpha.
Sorry. Say this again.
And xi is equal to 1 by mu minus alpha. That should be, yeah, this no. Phi equals to xi equals to 2 by mu.
So where is coming from? Let me not ask you to answer. What is the logic behind this?
So we said that the water filling condition that if alpha is smaller, then we have to make xi larger, and vice versa. So the equilibrium will happen when exactly both of them are same or in the same level.
For what value of I will these quantities be equal? Look at this. So simply xi is strictly greater than 0. The roundabout we are looking at it. This is nothing but it appears here in the subtraction. What do you want? Xi times is to be equal to 0. And what we essentially have is that either this is 0 or this is 0. If this is 0, then this better be greater than 0. You can look at it from this angle as well. So suppose mu is less than by alpha. When is this possible? I know that mu is greater than this total. When is this possible? Only if xi is strictly greater than 0. Otherwise, it's not possible. That much we can conclude. Then we simplify that. Xi is star. Xi is greater than. But if xi is greater than 0, what will the equation tell you? That mu is exactly equal to 0. will in fact be one more. Yes. The following one from if U is less than this quantity, because of this condition, it implies that xi is greater than 0. The xi greater than 0, Q better be. Okay. What more can I add? Here, what do I get? I essentially get take one. Five. So if mu is less than 1 by alpha I, you end up getting what if it's more? That's only case. Only A. What is case B? B is zero. Very good. And why? Because we have boundary condition that exactly the review will follow by this too. Otherwise, this will lie like it. We will go what we get. Now all xi star is equal to 0. If mu is greater than equal to 1 by alpha and what is this quantity? Can you put it back all together and get a final answer? Is everybody okay with this? Working? That's what my optimal answer looks like. Then something remains to be solved. Alpha I is unknown. Mu's are not known. How do I find the mu? We have this constraint here for variable. The summation xi is equal to 1. All that I need to do is to map this. Here A, so let me call it I belongs to S, where it is 2. This will give me my news, and I can keep going back and write down exercise. Can someone tell me if I give you this and ask you to implement, how do you implement this solution? Is everybody okay with the solution we got so far? Do people see the difficulty? How do you actually execute the program? Because how do you find x directly? That the s is the side where mu is less than 1 by. But mu depends on this. So if I keep increasing the constraint to 1 going to larger number, what will happen to this set S? Will the set S start increasing? There is a lot of indices I for which this will start becoming true instead of 0. Is that clear? Or the other way direction. So suppose I increase 1 from 1 to 10. Let's say I'm just increasing the constraint from 1 to 10. What do you think will happen to S? What is the set S for which non-zero xi? That's the set S. Now I'm increasing the constraint.
Nice.
Will I get S larger than S? So let's call it S1. Will S10 be larger than S1? Will S10 be smaller than S1?
This will be same, right?
Same. Why don't
Because the S is depend on the mean.
So what is mean? So as I increase my set constraint here, what is happening to me? I'm not changing the IDC right.
You're scaling.
I'm just scaling my constraint. So this program, going from summation xi to 1 is going to 10. What do you expect an answer to become from here? You expect an answer to decrease. Because I can apply larger, I'm not increasing the increasing part. They remain the same as. All I'm doing is allowing you to put more evaluation to the exercise. You can expect the answer to definitely change more events. And its object to be about to have. This level mu which you're going to maintain. See, that's indifferent to the indices R. It's a single level. That level will keep changing depending on what constraint you get. So suppose that you will start. What do you get? I belongs to S. 1 by P. So means writing S, so all of these are essentially positive. If I have written only index I, some of them will be 0. So what is this? This is nothing but mod S by V minus summation alpha I belongs to S equal to summing it. So what would mod S by V be? 1 plus summation alpha. So if 1 increases, what happens to mu? Iterative process, that's why I'm trying to apply your text. The S will start depending, how many S's are allowed there will depend on them, and what's the level mu also will depend. That's the problem. So now this will be S over 1 plus summation alpha I. So if you knew ahead of time which S will actually get positive power, this is the correct thing. Now you go back and check whether whatever mu you are finding, does it give you positive or non-positive? The way to start this, put S is equal to full set 1 to n. Everybody. Now you compute this one. For whatever values, this 1 by v happens to be smaller than alpha I, you remove them. So let's call that S is equal to S without the set for which you try to become negative. You recompute your name. And you keep doing it until you are with all the elements you got in S, everybody gets a non-zero. Now this proceeding will completely depend on what value of this one constraint is. That's the point. So if you were to write a program to install this, it's an iterative process. Because it's weird, you might not notice it, but it's a weird process. It's not as good as, so essentially, if it was this, I think that comes. Okay. What will we do? We do the level mu and 1 by. What does it mean? If this is large, means the value of alpha I is small. So this is on the 1 by alpha what I'm doing. The first one, let's say, is small. That means alpha 1 is large. So this is 1 by alpha. Just that. This level is determined by how much power I get. The solution is telling you is this much is the power xi allocated to index number 1. So just keep calling the power. That's where the physical interpretation problem comes. So this much amount of resource is allocated to channel number 1 or user number. Let's suppose this was 1 by 3. It would get so much, and so on. These guys who are above this level will not get anything. They don't belong to us. So everybody who is below this level belongs to us. Who is above the level does not belong to us. And these guys essentially, it's as if they don't even exist. But now, if I give you more and more with the constraint, what will happen? That this level will start going up. And because of that, possibly this will be below the level. At this point, it will start getting non-zero power. So that is why you start with all of S. You compute the level, you see whoever is excluded from it. You exclude all of them, and then you continue. That's the way to write this. So the process is called water filling. So it's as if this is a closed container, and these are 3-dimensional objects, and you try to pour water from top. The total volume of water poured is 1. So whoever is going to get the water is exactly whoever is below that. And that exactly that much is for the answer. And that's why you call water filling solution. So this the non-triviality comes in because that everybody below a level. So the level is exactly 1 by r. Below a level will get something from 0. Above a level will get nothing. So even though we know this set, like nice set of sufficiently conditions, it's not always possible to define very nice answer. This is one of the big parts. Questions? The final thing to data science. And we remember what the set of conditions. So what is my convex program? It is 0 times this side 1 of this. What is the condition? And x delta at that x delta strictly greater than 0 at the x delta. That's my steps. All it's demanding is there exists a strictly feasible. Nothing more. And the program need not be differentiable. To go from strong duality to necessity of taking we require that program be differentiable. But here there is no differentiability required. It's a very, I would say, very weak condition, not a very strong condition. All you are asking is that there should be strictly feasible. Okay, any idea what's going to happen? Why is strict feasibility so useful? see. Additionally, the matter of the load and is again a x delta equal to the so define two sets.
So is that granted needed or it is just for the sake of the proof easier?
Yeah, I think it's needed.
If it is full and the previous thing is equal to space is a singleton bind. Because
Eight is not a square, not necessarily square.
as a
That's what we ask.
the rotation form has no zero.
All we are asking for is full load. Yeah, otherwise you can, why even say anything? I'm not demanding that A is equal to B. If A is a square matrix.
26
And this invertible. Though there is nothing to stop it. We will define two sets, A and B. And we try to see what kind of set we have. It will be actually useful sets today. In some sense, the epigraph version of the for the existence x. Y of x. The u. Example of it, one. H. Why is this set not empty? How do you imply it? That's my problem. We're putting a one at that. So then, correct.
The
You
origin
can even say x, but sorry.
the origin is
0.
so U B T, right?
You will t
Yes, the 0 is
0 is what?
already
If 0 is may not be there. If 0 is the term, then right to minus. That need not be there. But you are in the right path.
getting the x tilde, get f1 of x tilde, h1 of x tilde, and f0 of x tilde is
Well, it's actually a representation of the power. And set B is even more interesting. 0, 0, S. That S is greater than P star. P star is nothing about. Okay. So what check is there anything nothing with A and B? You property. You can take which connects A and B.
it is subset of
This is subset of A.
this one is the
Optimal value of the product. These two sets clearly. Very important, but the set should be there.
that is the minimum value of the x naught. And
Another constraint.
Yeah.
Not after that.
Yeah, P star is the minimum value of the S naught, AF naught, and you are T is basically greater than F naught. So basically, if we add mean over both sides, P star is greater or equals to T. Then T S is greater or equals to T. So in that case, what are the flat? Equals to T.
Is it possible to have a counter result? Okay, yeah, I was about to say that. Is it possible for a common element between A and B? No. Very good, is that? Why are you talking? But there is that. From suppose I make a plan. That A intersection B. How would that goes? We can take some element that belongs to both of them. Yes. Let's take U, B, P. Yes. So now you plan that if it belongs to A, it cannot belongs to B or either way. Carry on. So
We will look at the third condition.
yes, if it belongs to B, what do we get? U is equal to B is zero and P is less than I star. That's by definition. Something has to go wrong here. What will go wrong? The third condition. Okay, why?
Because P star is already the
Be precise.
The least value of f naught x that satisfies those two conditions where f1x is less than equals to 0 and h1x is 0 is B star. So it cannot happen that like P should be greater than equals to P. It cannot be less than B star.
Well, give me the punchline.
Because P star is the optimal value that
Exactly. So if it's possible to reduce the optimal value, then only it's possible to find a T which is less than P star. Because the T is sitting over there. So it cannot be that T is less than P star. Is everybody okay with that? I write it, but I think everybody should see what's going on. That's actually not possible for T to be less than P star. Why is that? Because of the quality. VP belongs to A. If this is not empty, therefore there exists an empty. Well, this satisfies all my conditions, and I'm creating a value for which of 0 of x is less than equal to P. And somehow it's smaller than P star, which by definition cannot be. This is and now, by now in the course, whenever I find two sets whose intersection is empty, you should know what to do next. That's really one tool we've been exploiting over and over. Between a point and a set and between two sets. What are lines? What are cortex? Third cortex. These are cortex, right? Need not be strictly, but separately have. And I have distribution. Therefore, let that be. And not all the Okay. So far, so good. So what is the argument? So far we have not said lambda is greater than 0 or mu is greater than 0 or mu is greater than 0. Can we argue somehow that lambda is greater than 0?
Want to put lambda is bigger than zero.
Yes. See, from the hyperplane, separating hyperplane theorem, I don't get something. But look at condition number 1. What does it mean? Lambda trans, so see the transpose. Lambda mu, so lambda u should have been right. Yes.
So, the second condition,
Yeah.
so we know that u and v is 0. So mu t is less equals to lambda when you
Mu is greater than equal to R.
alpha, yeah, alpha, when we don't have when the value of
Doesn't
lambda.
matter, it is 0 and 0. For all
Yes.
for
So the impact of lambda was not there in second equation.
So this is
So in the first equation,
come from here.
yeah, we are so totally lambda.
Suppose lambda is greater less than 0. Then this will be true. That's what we can argue.
Yes.
For points in A. If for all points in A, this is true. What kind of set is A?
So is this is satisfies our program?
Yes. So suppose lambda was greater than 0. What kind of U's and P's are there? Will this constraint be satisfied? Is the question we should ask. If lambda is less than 0 or mu is less than 0. And looking at what type of elements are belonging to A. What type of elements belong to A? Things which are under something. Less than equal to 0, less than equal to 2 star. So clearly, I can take something large enough minus value there. So what can I not do with this question?
Lambda greater than 0, we can the value will not be a positive enough quantity that will revert the inequality from below to greater equals.
Let's look at this one. Two times t over the fact. A. So lambda is negative. And mu is also negative. Where will this go? I know that this is above alpha or fixed alpha for all possible values. Then this is a non-reducible. If
If UAT is in it,
yeah,
then for every U dash less than U dash VT is also in it.
okay, what are you saying?
U dash with
Dash B, T dash what is this?
anything.
For which dash is less than B.
Plus, no, U dash is greater than. Yeah, this also belongs to the large.
Okay, so that is true. So I'm only increasing. So if U is there and U times R, this will always be there. Okay. So I guess if keep increasing, with a negative sign, this will become times unboundedly large with a negative sign. And this will start to vary. So essentially both of them get negative. So when we end up with B, well, just by the definition, mu and V are zero essentially. So mu T is
Yes.
R. All right. And P is what in respect to P star? Here, any QBT implies what with respect to P star?
P is equals to P star.
Yes, and why?
Because the sets are disjoint, we have created that correctly. No, T is greater than P star. Because F naught is less equals to T. And P star is the
Now we
mean.
have more conditional TLs that was used to make them disjoint. Now what do I have? This the element here, UVT, T is greater than P star. So I anyway have this element for T less than P star. This implies that what is here? These are all the conclusions we will not so far. Well, headed if somebody gets annoyed. Essentially, you want the reverse direction of weak duality. Weak duality, what do we prove? That P star was greater than the function G. G lambda, comma, G mu. I want to flip the direction. That's what strong duality is. So where is that hiding? Just hiding in these equations. So is there a correction to this equation with respect to the Lagrangian? Some part of it is connected to the Lagrangian. And just keep looking at the definition of it. I can't keep going back. For any UV belonging to A, what can you say about the Lagrangian connection with the equation I pointed out? U is above Fi of x, V is equal to Hj of x, and what is T? Revisit your definition of A, the set A. I'll tell you something about what is lambda transpose U can be written as greater than or equal to lambda transpose Fi of x for all x. Similarly, what can I do with V? I can put the Hj of x, essentially is Ax minus B. And what would last term? Mu times T. What can I replace that with? Like that. What term is that? Okay, U is V equal. D is what? They all going in the same direction. If I ask you to replace the left hand side of this, what can you replace with respect to Fi of x or F1 of x, Ax minus B, and F0 of x? What relationship can you write with respect to this equation?
E is bounded by minus is bounded.
Keep looking at it.
E bounded by bounded below is not.
Yeah.
You are replacing with equality H1 by V.
Not saying that equal to.
Not equal to, I'm saying.
All I want is we want you to write the LHS in terms of the Lagrangian.
Lambda transpose F5 plus mu of
And
H.
how did you get to that? It's not equal, right?
No,
It's not equal. Greater than or equal to what are you saying?
So I'm saying that u is greater than f of I is equal to u, right? So lambda transpose f of I is less equals to lambda transpose u. Hi is equals to b. That means
That is the X minus B, so that
yes. And the last term is if not f0 is less equals to t. So mu is less equals to t. Mu f not is less equals to mu t.
Your times
so what do I have here? Let's just write that. Can somebody just read that for me? Lambda transpose U plus mu B plus mu D equals to. Let me not write that. Just tell me what are you going to replace this with? I have that. You get it. I want you to write this in terms of the Lagrangian. That's all I want you to do. What is the connection that we just write? Calculation of A. This to that person. U X.
But this is true for all UV.
On unity belong to A.
Yes, so just take the increment for the increment also it has been true.
Any.
Yeah,
Okay.
if you just increment over UVT, then also the relation is true.
Yes.
So when you are taking the increment, that U will be replaced by A5.
Okay.
U will be replaced by HJ
Okay.
and T will be by F0.
Okay. And I do all that. What do I have extra condition from D? Alpha is also greater than or equal to mu is. Mu is. That's what I get. Now, so we can see that this is nothing but Lagrangian, except for some extra terms. Yeah. What is the extra number?
Mu times Lagrangian expression function.
So, mu is getting multiplied by only one.
It's not very new common outside.
And why should I have divided?
But it's fine.
Which I have shown. That mu is greater than divided. Okay. Why is this equivalent to the reverse wave duality? Remember what will wave duality show us? The G of we're showing the reverse direction. Except in this G. What is the definition of G? Hello. X. Oh. So what?
Increment we get G of lambda by mu is also greater than equal to B star.
If you move over X.
Yes.
Okay. So. What can we conclude?
Then G of lambda from mu is also greater than equal to B star.
How are you getting rid of the
It's
It doesn't matter.
It's a free variable.
It doesn't matter. I can just replace it with whatever I want. So what I was shown, exactly shown, the reverse direction inequality, as long as what? Mu is strictly greater than 0. I have not handled the case when mu is 0. I can't divide things when mu is 0. All I knew was mu is greater than or equal to 0. When mu is strictly greater than 0, all of this is fine. We still have to grapple with the case when mu is in fact equal to 0. That's like the dirty part where all this technical conditions are actually required. That it has full row rank. You're not yet used, you should have objected, you're not yet used the status condition at all. Alright? You have not asked for a strict feasibility. Even to show the separation there, I didn't demand that they should be strictly separate. That's why it should be a strictly feasible point. All that comes in to handle the case where mu is equal to 0. Yes. Mu greater than 0. Now, under the. If you will try to argue that is not possible, you get a contradiction. We got all the technical. Parameter. Or this. If you know somehow artificially that the mu you are going to get is strictly greater than 0, don't even need state. For the problem you are considering, you will show that mu is always greater than 0. You don't need it. You will have strong. Okay, so now we'll appeal back to all the conditions we got so far. So these conditions are true for all we have said is mu is greater than equal to 0. This is true, then mu is 0 as well. So this term will just drop. So what will I get? Lambda times u for you can go here. This is also all of this is true for mu greater than equal to 0. We already handled the mu greater than equal to 0. Now look at mu equal to 0. This term will drop out. This will be greater than equal to 0. That's all we have. So lambda x plus mu. So from status condition, what do I have? Existence of what? There exists an x tilde for which y of x strictly less than 2 and x tilde. So if I evaluate okay. Where the fallacy that we are going to get. So this is true for all points x. So I can apply it to x tilde. But x tilde also satisfies this. Lambda is greater than 0. So what does it mean? No, so what it means something. This is true directly from 1. Right? Any x tilde which satisfies x tilde equal to b has this property. But I know in addition that this is strict feasibility. So what has to be, and lambda is greater than 0. So what does it mean?
F1 of x will be x tilde of
F1 of x tilde 0. Go now. Wait for this. Lambda is
No,
lambda is
that is
greater.
greater equal to 2. If one of x tilde.
the only possibility is that lambda is 0. What we have shown before is lambda is greater than equal to 2. This implies lambda is because of To be clear, I'm just applying, evaluating one for x equal to x delta gives me this. But x delta also satisfies the property of f1 of x delta. It's strictly less than 0. So only when this can be true is when lambda in fact is 0. Oh, so now I want to lambda equal to 0. There is no contradiction yet. Now what? Remember my hyperplane, okay, so lambda mu and mu not identically 0. This is 0 starting from my case. I've shown this to be 0. So only non-zero variable, because this is non-zero, this better be that mu is non-zero. So if mu is non-zero, what is this? That's all you have to know. So all we are going to show that this itself is non-zero. Now take mu not equal to 0. Try to go about it. Where does mu affect? Mu only affects via. See, lambda has already become 0. So this equation has become essentially mu times ax minus b greater than this. Still you don't use the rand. Will come to that's all is remaining. I also know I didn't say it, so I'll say it now. Something is needed. So the interior being non-empty. But we'll come to that. So all we have to argue now. Mu is not equal. This is 0, this is 0. All this vector is not 0, so mu is not equal. Now if mu is not equal to 0, what? Equation 1 is true for all x.
So if mu is non-zero, then all the coordinates in the new must be non-zero.
Not all, some of them could be 0, some. It's not identically equal to 0 always. If you go to the one equation 1, tell you already we have proven that lambda is 0. We have that mu times ax minus b is greater than or equal to 0. Now we also have that mu is not equal to 0. What more can we say? And what about x tilde? When x tilde evaluated at equation 1, because it is ax minus b, ax tilde is b. What does it give you? It is exactly 0. So now think of the interior of the domain to be non-empty. And x tilde sits inside the interior. So what kind of points exist around x tilde? So this thing right on. X tilde is what does x tilde satisfy? A tilde equal to b. Look at its neighborhood. Does there exist point which new transpose things? There is zero. Let's write this as new that's what x tilde does. So around its neighborhood, there should be some x which has this less than equal to 0. Yes. Maybe
No,
Why?
A has full rank, right?
We not yet used that.
Yeah, A
It
has.
will do the punchline, it is also not possible.
No, I'm saying so. If a so the solution space in not only zero contains a mode point, it's a subspace,
But we not do subspace. Subspace is too much. We're not saying anything about subspace. All we are saying is the interior. Where which X star X.
so my idea of thinking that if we are taking a ball around X tilde,
Yeah.
okay. So if A is not a full rank, then the solution space of the equation Ax equals to B
Can
will
we, yeah,
will
can you not give the fact that X, because that's the next punchline we need. For the moment, all I care about is at X tilde, this equation is true. When there exists a neighborhood of X tilde when this is true. As long as the interior is non-empty. The next slide requires the either put you trying to. It means something. This is true unless we ask. They transfer. This we know. We get the very as only to equal to the by the very definition of external interior of the domain. Therefore, the system X as that you transpose the X must be equal to unless a transpose is equal to zero. What happens when A transpose B is zero? Essentially, B belongs to the null space of what will happen if this is possible.
If this move to be non-zero, A transpose will have a non-zero.
You go right, we transpose A is the same. So what's the else? What I written is concrete. Understandable or not is the question you ask. So if this is true, what happens in the neighborhood? Either all points map to zero, which essentially means this, or there exists a point X for which this is less than zero. This is precluded by the fact that A has full order. And this is precluded by our previous equation, which requires that this is greater than zero for all points. So either way, you get a function. So each of them we use, but only for the case when we use it. It is okay what is going on. So this is zero. Because around the neighborhood, everything is zero, provided this is zero. So all of it just the whole interior just belongs to the null space of A. In which case this is not. And then I can get what I want. Or I will get a direction which this is less than. But both of them are precluded. This is by the technical conditions that A has full order. By this, what we wanted. Either way, we get it. This strictly. That's all. This last bit is slightly different. Rest of it is very nice. Okay. Any questions? The book actually has multiple ways in which to explain duality. So do read it. Maybe after the exam. But try to acclimatize it. It's just a few people told for you to actually work.
So from the last class, this slackness condition Yeah, boils down to it are giving you another way to achieve the strong duality basically.
Strong duality implies complementary statements. If there is strong duality, then complementary statements works. It's not the other way. That's the application. To establish the strong duality words, one possible way is to use X. But that's not all. This is sufficient. It doesn't say that if there is no such point at which the constraint is strictly feasible, there cannot be strong duality. It doesn't say. There's no
No, for the sufficient condition, we needed that A is full rank. So
It doesn't say that if it doesn't have full rank, something will go. For a particular problem, you find out. You will not have this proof, but these are not economic. But the KKT, there again, strong duality implies necessity, right? Sufficiency directly comes from the balance. But the whole idea of how to think about probability and that you should just implement like this. It's a very deep and beautiful idea. It also helps in academic writing down. Suppose you don't know, like you have a hard problem for which you can't find an infinite answer. You write a dual, fatal lower bound, and then you run your program and you find that the values you're getting are close to that lower, 2 times, 3 times. You can actually eventually start. It gives you somehow a handle that how low can you actually go. You're trying to minimize it. And very often the dual program is actually nicer to compute or to find the non-trivial lower bound compared to the parallel programs. You already said the dual programs always concave, irrespective of the parallel probability convex. So there's just too much to take away from this one chapter. So like one thing you carry from convex optimization of this course is one thing. The concept of duality. Okay, actually, get your hands dirty. Of course, the homework I will set up in this. Like it or not, you get your hands. This is one of the most beautiful concepts. After the midterm, we essentially now get down to doing algorithms, how to actually solve convex problems or even non-convex problems. Looking at the convergence rates, how to work on static fixes, getting the convergence rates. That's what we do. Rest of the class, not 8 possibilities. All right, let's stop here.